mentally, math!
Let's get mental!
Alright, give you a few minutes to get out ahead of me. We know the drill. Yo!
We haven't actually had a lot of estimation.
Yeah, they haven't done that in a while. You see, they want to sneak it back up on you.
What if they
Now
know-
that
what if they
people
know
are
you're
ready
catching
for
on?
it.
What if they know you're catching on?
Yeah, they know that by now people are catching on, so they're gonna take a pause from it just to let you lead you into a false sense of security.
And after strike is right.
And then they'll strike again. Yes.
Strike again.
Okay, and yeah, today we will. Today's about learning rules. Essentially, there's just a couple of rules to remember. It's a formatting thing. So what does it mean when there are negative exponents? And then scientific notation for teeny tiny itty bitty numbers. So another way of getting rid of a whole bunch of zeros, but in this case it's getting rid of a whole bunch of zeros if you've got a whole bunch of zeros after the decimal. Like it, anyway, we will get to that. All right, so looking at A, I can think of that as 32 times 4. Just dividing one by 10 and multiplying the other by 10, which would be 120 plus 8. Okay. 128. I have no doubt that you have already finished your mental math. All right, so then this one is 3 boingies. So boingy, boingy, boingy. Little scientific notation right there. Then, okay, so this ratio, it's just times 4. So 7 times 4 is 28. And metric conversions. That's half of a liter because there are 1,000 milliliters in a liter. So 5/10 of a liter. Easy peasy lemon squeezy. All right, then this is basically 225 minus 125.
Wait, this is the same problem from yesterday.
Nope, not quite. The other one was 625 minus 225. So this will be 100. And then 1/5 of 25 is 5. So 2 of those would be $10. Dollar bills. Yo.
I think there was another thing. It was in the when we were doing the written practice, all the odds. There was a question with exponents. That you had to solve, and part of that question had 15 squared minus 3 cubed.
Oh.
Which is basically like this problem. And then it was 100 the root of 100.
Okay, well there's a lot of spiraling with this with the Saxon. It kind of goes in circles and brings you back and reviews things. I think they do it on purpose. So this would be to find the range. You would just take the largest number and subtract the smallest number. And 87. Then starting with the number of pounds in a ton, 2,000. Random arbitrary number, divided by 2, 1,000, minus 1, 999, divided by 9, 111, this is strange, minus 11, gives us 100, square root being 10, then divided by 2 is 5, and then that divided by 2 is 2, 5/10. Tens. That's kind of a weird one, wasn't it?
Yeah.
I thought that one was a little weird.
It's like 999 111.
Okay. So what? Is there a question? What's up?
Not really.
Okay. All right.
Nah.
Okay. All right, so lesson 57. So the first thing is rules about exponents. So, who remembers, though I think I'm pom-pomless at the moment. I'm just going to have my respect and admiration. Who knows what the rule for a zero exponent is? Yeah.
I think it'll always just be 0.
Nope.
What?
It's okay. What do you think?
2 times 1 is 2.
Huh?
It's 1.
It will always be 1.
How's it 1?
Huh? It will always be 1.
How's it? Oh,
Huh? Well, it's sort of a division problem. Basically, it looks like this if you conceptualize it. It's 1.
Get it.
Okay, well, it might make a little bit more sense looking at what the rule for negative exponents is. So, okay, so let's look at B. But anyway, just remembering the rule, just remember anything with an exponent of 0 is 1. So, 1,567 to the power of 0 equals
1.
1.
What about
So-
like 1 quadrillion?
1 quadrillion?
Power of 0.
Yeah, any of that. 1. Yes, it always ends up being like that. So, so the rule for negative exponents is the negative exponent means it's going to be a fraction. Okay, so the negative exponent by itself it's like this, and then whatever ends up in here is your next step. So then your next step might be to think of it like, so now that you made it a fraction, then it would be 1 over 3 squared. So the answer to B would be 1/9. So this is a rule. It's kind of one of those, if you ask, well, why is it like that? It's kind of one of those, we capitalize the first letter of a sentence. This is, so it's just sort of a rule of formatting. Yeah?
So, can't you just move the decimal 2 places forward instead?
No, because you're thinking in terms of, now, if you're talking about 10, absolutely yes. But not with any other number than 10 and a negative exponent. So you are leading us right into C.
Right into the...
So what you're saying absolutely applies to C, but that's because it's 10 with the negative exponent. So that bounces your so essentially, okay, you next.
I don't get how it's like. I don't get how B is 1/9.
Well, it's not a thing to get or not to get. It's a thing to memorize what the rule is. So the rule is that if something has a negative exponent, that means you are turning it into a fraction with a 1 on the top.
So
And then your number and the exponent go under that. That's the rule. So there's nothing to get or not to get. It's just that is what you're supposed to do if you see that.
Is that just a rule?
It's a rule.
So does that mean...
So 3 times 3 is 9. So that gets you to your next step of 1/9.
So that means C is 1 over 1,000?
Yes.
Oh.
Exactly. So, and we can express C. We can express C a couple ways. So yes, we would express C as 1 over 10 to the power of 3, which would be indeed 1/1000th, or you could, and then so the next rule here is talking about to say the next rule is going now, and you could also, of course, phrase this as 1/1000th, right? So either way. So this kind of segs into what the whole rule with the scientific notation is going to look like. So what if you've got, really small numbers to work with, like the size or weight of an atom? Something where you're going to end up with a gazillion zeros. There must be a way to do shorthand for that, right?
And then after like a gazillion zeros, you have a 1. Or 10 to the power of negative a gazillion.
Yeah. So, you don't want to be trying to work with this number, right? That's silly.
Yep. After you read through all the gazillion zeros, you find a 1.
Well, that would be sad. That would be devastating. Okay, so the rule for the scientific notation is it is the same as the rule for scientific notation with without the negative exponent, except you're moving your decimal to the left, not to the right. So say we're starting with this number, but we've got 10 to the power of negative 8. So you're going to bounce that 8 times to the left. 1, 2, 3, 4, 5, 6, 7, 8. That's where your decimal will go. You put a 0 on the other side.
Mr. Petrie?
Uh-huh.
If it works here, then why didn't it work with the 3? The previous problem.
Because you can think of that as this.
I'm not really understanding.
So let's keep focused on what we're doing here. So
no, I get it. Oh no! In the last problem, it was exponents. In this problem, it's scientific. It's a scientific standard.
Yeah. 2, 3, 4, 5, 6, 7. Okay, and then 6, 3. Okay, so essentially, it's the same sort of rule of with scientific notation. There has to be one whole number to the left of the decimal. Anything else goes after, or goes to the right of the decimal. Okay? So that's always the same. The times 10 to the power of is how many boingies you've got to put it into standard notation. But if it's a negative exponent, it means your boingies are going to be to the left. Does that? So let me see how we're doing. Give me a 1, 2, or 3 about how you're feeling with that.
So,
okay.
Mr. Petrie.
Uh-huh.
So basically, negative, move the decimal left. Positive, move it right.
Yes.
It's like a number line.
Yes. Think of it like that. So maybe it might help if I did this with a slightly more simple one. Okay. Thank you for the feedback. Okay. So let's say let's say 3 2/10 times 10 to the power of negative 3. Okay, so the rule for that is if I want to now. So this is scientific notation, but if I want to convert this into standard notation, then this negative 3 means I'm going to bounce the decimal 3 spaces to 3 digits to the left. So it'll be 1, 2, 3. And then that's where my decimal is going to go. So I have to put a 0 on this side of the decimal. All right, I can fill in my boingy spaces there. So essentially, this would be equal to that because we moved the decimal 1, 2, 3 spaces, right? It's just a way of writing numbers in shorthand that would normally have a whole lot of zeros, but we don't want to write it like, you know, if say it was 31.
What?
Do you think I want to write that number? No. So it's a way of writing it so that I'm not covering my page with zeros, but that we can convert it back to a regular looking number. And so the rule for it is just that's how many bounces you're doing to the left. Now if there is no
Right.
if there's no negative, then that would mean then I'd be putting that to the right. So that would be 1, 2, 3. Right. So 3,200 if there was no negative number, right? Because then we would send that to the right. But with the negative one, with the negative exponent, we bring it to the left.
So if you had 3.2 times 10 to the power of minus 31, what would it be then?
What would that look like? Well, okay, well, let's see. So, we have 1 for that. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Then 1 for my first boingy. 31.
Wow.
That's what that would look like.
Nothing.
It's just a totally ridiculous looking number, right? So that's why we have the scientific notation, so that if we're dealing with super tiny numbers, then we're not filling our page with zeros.
Okay.
Yeah?
I think this is when it becomes really useful, like that example of negative 31. Like, if you had like negative 1,000,000, that would be sad.
Yes. I wonder what could be that small.
And you read through 1,000,000 zeros, and then at the end, like I said, you get a 1. After 1,000,000 zeros,
Mhm.
you read through it, and you get a 1.
Well, that'd be a very, very small amount of something. Indeed. Okay. All right. So, knowing what you know, see if you can figure out how to write this in scientific notation. We'll see if you can do it first, and then I'll try it. All right. Try to write that thing in scientific notation. So remember the rule for scientific notation is 1 whole number to the left of the decimal. That everything goes afterwards. So you're going to start with 3 3/10 times 10 to the power of negative what? Well, you just count them. Just count your boingies. I'll take a couple of deep breaths, let you get out ahead of me. Are you just wanting to blurt the answer? So I'm probably going to want to demonstrate the answer. What?
So, like, I have a question. So, like the last problem, when you're doing the multiplication, like when you to the left, does it only, or the right, does it only work for the number 10?
Yes, it only works for the number 10. So yeah, we were talking about that before. Because you're either multiplying times 10 or you're dividing by 10. Which that moves your decimal back and forth. Any other number, you're dealing with complicated equations. Because it's just, yeah, we're just moving our decimal around if we're working with 10. Anything else, that doesn't work at all.
So if it was like 9 and like 9.
Then better bust out a calculator, my friend. Yes.
What if you were to do a multiple of 10?
Multiples of 10? Well,
Sorry, as in like 100.
what about it?
Or I was just wondering if those would work.
Well, It would, but that wouldn't be scientific notation. Yeah? I guess that would be double bounces or something. Yes?
I wish I could work there, but wait. So when you put the chopper, when you put the I, you have to put it. It's in a minus form, right?
This will have a negative exponent times 10 to the negative something. Okay, so let me count my boingies here. 1, 2, 3, 4, 5, 6. All right, so we'll end up with 3/10 times 10 to the power of negative 6. Ta-da! See, it's simple. You just need to remember the rule.
Now it's a 3 for me.
Huh?
Now it's a 3.
Oh, excellent! That's great. Okay, I love that. A light bulb. That is fantastic. All right, and this next one's kind of insulting, actually.
Yeah.
Okay, don't throw things at me, please. So is 1/1000th greater than, equal to, or less than 0?
Oh my god.
Yeah. Well, but you know. Look, there's a negative. No, there's a negative. There's a negative. Doesn't that mean it's negative? Doesn't that mean it's less? No, it doesn't make any sense at all. No. So no. This is basically just 0 and
So sad, 0.
1/1000. Thousandths. Yeah, I totally meant to do that because I'm like totally cool. And so I mean, 1/1000's pretty small, but it's still more than 0, right? Okay, good talk. Okay, and that's today's lesson.